goes this way. Therefore, this is A. That's the definition of a dot product.
That makes a lot more sense now.
I thought it was a lot worse.
Straight dot. When he first introduced this, when he first introduced it to us,
I think it's back then.
And now,
Which I still haven't figured out.
for this one, it's straightforward. It equals the magnitude of the field, multiply the magnitude of the area, then multiply cosine theta. That's how you change the vector calculation into scalar calculation. And the solution is called flux. And the flux is a scalar. Flux doesn't have direction. Because after this multiplication, solution becomes scalar. No direction.
So in order to solve the problem, we have to put it in a scalar form, right?
Yes.
Yeah.
Okay, therefore, the example here, try to calculate something. I tell you, you have a uniform field over here. Goes from the left to the right. Okay, this is the E field. I can tell you the number, for example, 10 Newton per coulomb in the X direction. Okay. If I put this area this way, not perpendicular, see, tilted this way, which means my paper goes this direction. Okay? You look at the paper this way, okay? And I tell you this angle is 30 degrees. This is the area A. So what is the flux, electric flux in this situation?
It's the dot product of E and A.
Okay. And I tell you the A is 10 meter squared.
So it's 10 times 10 times the cosine. Is the cosine of 30? Yes, because both angles will be this. Times.
Here we have a problem when you do the practice. We know exactly the direction of the field, right? You see, it's labeled clearly, right? So what do you mean by the direction for area?
We just must orient.
You see, this is the area. What's the direction for it? Inside the plane or the other way?
Must assign
You have
direction.
to, yeah, you have to make a decision, otherwise people get confused, right?
Right.
You have two options. One is you said this is the direction of the area. The other way is you said this is the direction of the area. Either way is fine, right?
Yes.
But people did this before. It says the direction of a field in physics, for example, you have a tiny area here. The direction of it is what? It's the normal direction. That's the direction of this area A. Oh, you can go this way, you can go the other way. Either way is fine. The direction of the area must be perpendicular to the area. Okay? Therefore, for this paper, I put it down this way, right? What's the direction of it? It goes this way. Or go backward that way. Either way is fine, right? That's the direction of A. Therefore, are you sure this is 30 degrees?
No.
So we will choose the complementary angle.
I don't know. Look at the picture. The
What
angle
would be
between
90.
the two vectors, E goes this way,
Okay.
A goes
If
this
we
way. What's
choose-
this angle?
If we choose this direction, is the
The same one, right? I thought they're
60.
equal. Are
The
they not?
straight line,
Isn't the
the straight
same
line is
thing?
180. If we take
Draw.
30,
Are you sure this angle equals 30?
no.
Why not?
I mean, is it the direction from the perpendicular? Like,
Yeah, this direction is perpendicular to this line.
What are we doing? What, are we comparing it to
if
A or
it
comparing
is,
it to the?
then it
Yeah,
is.
we know this angle 30. I want to know this is 30 or 60. Or you're not clear, you draw a line over here, parallel to this. So this is 30. What's this?
Sorry.
This is 90 degree, right?
Yeah.
Okay.
Therefore, what's this?
60.
This is going to be the same as this, right?
Yeah.
Yes,
So
it's
it's
60.
Okay.
You figured.
Therefore 60, right? Therefore, you put down 30 degree, it is wrong. You have to make it clear. Therefore, here must be 60. Oh, that's a simple geometry. You must have learned that before, right?
Yes,
In the
it's fine.
theory.
I
was
just
gonna say,
didn't know
it's
we
never
had
great.
to assign a direction.
Yeah, it's been a while.
It's the same will never tell me I'll be using this for the rest of my life.
There are so many other
Okay,
kids that
therefore
don't
you
know
got a
if I learn
solution.
anything like
What's the unit
Sounds
for this
crazy.
parameter?
You
Can you
have not
produce
taught
it?
us this.
What's the unit for E?
E is.
Definition is
NC, the NC thing.
F over test charge, right?
Yeah.
So therefore it's Newton per coulomb. Then multiply A area.
Meter.
Meters?
Squared. Squared.
Squared. Therefore you combine them together. You call it Newton times meters per coulomb. That's the unit. And as one of the homework, find out is this combination having a special name or not?
N squared C.
Okay.
Probably it has a special name. Well, it's in the book, you can read it, okay? Otherwise, if you keep this one, it's still fine. All right, so if this is clear, there is a particular situation. You have an object like this. This is 3D. Okay, 3D object. You have field lines coming in and moving out. You have another line coming in, moving out. You have a third one coming in. Okay, coming out this way. I can tell you, for this closed 3D space, there's no charge inside. Of course you have electron, proton, but no net charge inside. Do you think those lines are continuous inside?
Yeah.
Or 3 of them going in and only 2 of them out? Is that possible?
No.
Both
Because the
zero.
condition is this one doesn't have any net charge.
Charge passes through?
All the line you mean pass through, not stay at all, right?
Right.
Okay, you're right. If this one carries charge, the situation is completely different. Because as you learn, those lines send out by the positive charge and stopped at negative charge, right? Therefore, if you have a tiny negative charge over here, some of the line must end up over here, stopped,
Yeah.
right? Not all of them, some of them. Therefore, some line will be missing. Or if you have positive charge inside, what's happening? 3 lines coming in, how many lines out?
2,
No, this one is generating
3, 4.
5.
generating lines. Therefore, more than 3 will be going out from this
Yeah.
space, right?
Yeah.
Okay, that's the point. unless you have charge there. Otherwise, those lines are continuous. And just penetrating this space never stay inside. Okay? And another thing is, no matter how many electric fields around this area, if you pick up one point in the space, I ask you, what's the direction of the electric field at this position? Will that direction unique? For example, I said this is the direction of the field at this location, no matter how many electric fields around this point. And anyway, this is the vector sum, right? You add everything together, you got a solution like that. Therefore, this direction must be unique. At one location in the space, not possible the field has two directions, right? All right. My question now is, you have one electric field line goes this way. You have another line goes this way. My question is, right here, is there a cross point between the two lines? In other words, are two electric field lines can touch each other in the space?
Yeah.
Wouldn't it depend on what charge is there?
No charge.
No charge.
Just a pure space. No charge in this space. Just two lines right there. Are they touching each other or not?
No.
No, I'll
They
say
bounce
no,
off.
but they're
Why not?
They're coming infinitely close.
Yeah.
Well,
they're
yes,
repelled.
they can be even close, but no touch.
Yeah.
Why?
Because they're the same charge. They're repellent.
No charge. I told you.
No, the arrows, they have no charge either. Only one thing can occupy space at one time.
Okay,
So
that's a
how
good
can
point.
two things be there at the same exact time?
But you didn't explain it clearly. The idea is good,
It's like laying two pieces of paper on top of it. Like,
but they are touching
But they're
two
coming,
people
it
together,
can
right?
be close.
but they're coming from two different sources. The electric field is coming from.
Oh, that's fine.
The answer is
But
no.
that's
They
Well,
don't-
that's
But
not
that's
the
how
reason
you
they are not
define it.
touching each other.
But that's how you define it by the particular particle charge, right? You define the electric field by a particular.
But even
Because
these
it's
two
the
lines
smallest
are
thing
coming
ever.
from two different sources. Why not? They
They're the
touch each other. Why not?
Smallest thing ever.
Because they would repel, or no, they wouldn't.
There's no charge. It can't
This is the
occupy
basic
space.
reasoning here. And that's why I make this clear first. In a space, any point of field only have one direction. Can you apply this here?
Well, yeah.
Yes. You see, these two lines are labeled by arrowhead. If you said that they are touching each other here, along this line, the direction is this way, right? Then along this line, direction is this way. Which means in the space, one point you have two directions on the field.
This cannot happen.
That's crazy, not possible. Therefore, they never touch each other. Therefore, in a space, even you have countless number of electric field lines, they never touch each other. Okay? Never touch each other.
And it's all because they have to have a unique direction.
Yes. The
Okay.
point is, one position you have only one direction on the field, but if they touch each other, which means you have two directions on that position. That's
This
not
is true
possible.
in real life. This is true like the Earth. You know, the Earth has magnetic fields.
In not only the Earth, the whole universe.
I know, but I mean, those magnetic fields, no two fields would ever touch each other.
No. Never touch each other.
What happens all the time? People go through the field.
If they touch each other, the whole world will disappear. Not
This is
possible.
lost.
Shy.
Okay. Now we go to the Gauss's law. Gauss's law is one of the smartest discovery in physics.
If not,
And you cannot enjoy the beauty of Gauss's law unless we apply calculus.
I
Otherwise,
think so. We're not mathematicians.
so if you want to go